Okay, so we continue from the last EP that to show that limit of these functions does not exist. The techniques is the first techniques that we will show the limit on of this, right? The theory states that, right? If we can show the limit, right, on this part of the function xy, right? Like we can find right on the curve C1, okay? And the value does not equals to the limit, right, of this part when xy equals to on the point C2. Okay, we also have the first technique or the theory state that if we can find the limit on the curve C1 and the curve C2, there are different values, right? So we can conclude that the limit of these functions approaches to the point AB, right, does not exist. Okay. Okay. So let's see. We have to find the curve C1 and the curve C2. So easier, right? Maybe just the curve can be like a line, or you can got that, right? It's a symmetric line. Or it's just the parabola, right? Something right to me, like this. So find like this, okay? Or you can find like the negative, right? Or you can find like also the negative, or the parabola, right? On the left, on the right, or above or below, like y equal x squared, right? Or y equal negative, for example, right? And so on, maybe like x cubed or like a polynomial, okay? Okay, so let's see on these examples. Okay. First, we have to notice that what is the highest degree of the top term and the bottom terms that we already combined. So you can see, right? The top term is the functions the polynomial x times y. Then the highest degree of the top term is 2, right? And the highest degree of the bottom term or the numerator is also 2, that both are equals, right? So if that both are equals, suppose most of this case does not exist. But not for every case, just also have the exception case, okay? But most of that, the highest degree of the top equals the highest degree of the bottom, right? Most of them answer when the limit, the point xy equals to 0, right? The most answer does not exist, but not for every case, okay? So we claim that it also does not exist, okay? So let's see how to prove, okay? So we claim this and use these theorems. Let's see. So we have to find, right, the limit of these functions on the curve C1 and C2. So I think it's easier when it's highest degree of the top term and the bottom terms are equal. They must be choose the line that the same degrees, okay? And after that, we just replace the term y, the term x, or the term x is defined, doesn't matter, okay? Okay, so if we replace y with x, so you got it, right? So x squared over x squared plus x squared, which we can simplify the terms, and x squared can cancel, okay? Then it's left only the constant terms half, right? And the limit of the constant also equal constants, okay? The others curve, we should choose that to get not equals to half, right? So that we can also refer to this theorem that the value of the limit on the curve C1 and C2 are not equals, okay? Okay, so easier, right? Just choose the opposite, right? So on the right 2, we just choose x equal to the negative y. Okay, then we found that if we replace x is equals to negative y, right? So you got that, right? This is the negative y, right? Time with the y, okay, and divide by y square, right? This plus y square, which also equal negative half. Okay. Well, we found that both are on the curve on the right. L1 and L2 are not equals, right? So then we can conclude that this limit does not exist. So just the main ideas, right? How to show. Okay. So this is the theorem that you should just use, right? This theorem, right, to prove. Okay. Then the second techniques are the next theorems. We have the functions that the degrees of the top terms. Okay, so let's see. We still find the limit which the xy equals to 0, 0 of the terms. Let's see the easier one. X y square over x square plus y square. Okay. So let's see. The highest degree of the top term is 1 plus 2 equals 3, right? And the highest of the bottom term is still 2, which the highest degree of the top terms, right? I mean it, right? So this is ready for that. The highest degree, right, of the bottom term, right, or the numerator, right, is equals the highest degree of the bottom term, right, or the denominator, right? So normally when we find the limit, most of the case just answer doesn't exist. But this, the highest degree of the top term, right, or the numerator is 3, which is greater than the highest degree of the bottom term or the denominator, right? Most of the case answers it's this equal 0, because if you cancel something, right, just left and the top term, and after you replace this term, right, is equal 0. But they also have that exception case, but also it's equal 0. Okay, so we claim this limit is equal 0, and we have to prove that. Okay, so we just choose the theorem. Okay, so you can see in your note, right? The theorem states that you have to check 2 conditions. So the first conditions, you have to check that the limit of the, okay, so I'm just write into term. Okay, so you have to find, okay, suppose that you have to find the limit of the function h, like this. Okay, so I write in the term of the point a, b, right, in the general. And then we separate, okay, the function h in 2 terms of the products of the 2 functions, I mean, right? We can separate function f in the 2 terms of the function f and the function g. Okay, so this means that we can write would try to find function h, right, in the products of the 2 functions f and g. And then the first condition, we find that the limit of the function g is also equal 0, right? Anyways, the condition 1 and 2 you can split, right? Or you can swap. So the limit g can be like a condition 2 and this 1, doesn't matter, right? Okay, first check that one of the limit of the g is equal 0. Second, check that the function f is bounded. So what this mean? That means that, right, the absolute of the function f which less than or equal to some term m, okay, like m is any positive real numbers, okay? And one thing is that have to check for every point in the domain of the function f, and can you remember, right? So we also have like from the definitions, right? We also have like a delta, okay? So we have to check that from the theorem, right? For every the point x, y in the domain of the function f, and when we find like the point, for example, right? If we have the point A, B, right? Oh, okay, so suppose that we write this right at any point, and this is the point A, B. So we have to find, right, the delta, right, this at any point x, y. So we have to consider, right, every x, y minus, which is the less than delta, okay? So that means that, right, or we can write this term in the term of the look like this, right, or distance between that the point, any point x, y also in the ball of the point A and B, and not distance more than delta 2, okay? So it could be check just a slightly bit like we have to check for every point x, y in the domain of the function f, and the point that not too much too far away from the point A, B, that means the limit x, y close to the point A, B, okay? So if we have that two conditions, right, this is the one, and this is the bounded, then we can conclude that the limit of the function h or the functions f times function g is also equal to 0. So this is just the theorems, okay? So if we have these conditions, okay, and these conditions, right, when the term f is in this, then we can get that, right, the limit of the function h also equal 0, okay? Okay, so let's see the examples to make this clear, okay? Okay, so we go back to our example, right? Okay, we have xy squared over x squared plus y squared. Okay, so we would like to check that whether, right, this also equals 0 or not. Then we have, this is our function h. Then we separate, right, what is the function f and the function g. Easier to choose that function g must be include the bottom terms and with the same degrees, the bottom term. So we choose, this is the function f. So this is the function f, okay, that degree. And then the rest is also the function g, okay. So this is the function g, okay. Okay. So that means that, so we give that, right? We let, so from we start, right? Our function h is and the function f is and function g. Okay, so easier, right? The first conditions. We have to find limit easier of the function g. Is the limit, okay. Just write more, right, to make sure function g is also equal to 0, right, because we can replace x with 0. The second conditions, we would like to find that our function f must be bounded. Okay, so function f is equal to the absolute of x. Well, since it's the in the power of second, right, then both still can positive, so we get it. So how to find which term is less than this? Okay, so let's see, just for the note. X squared always positive, right? Since x is the real numbers, the products of the real numbers. And if we plus with and y squared also positive, and if we plus x plus y squared, right, also greater than, right? So if y squared, so x squared plus y squared, right, also greater than or equal y. Okay, so we need y. Okay, you can see. And this is also is the positive. And when we talk with this, when we would like to find the limit that close to 0, 0, right? One thing we have to make sure that x and y must be not equal 0 with the same time. So with this is also greater than 0, right? Okay. So we can so this we can divide, right? If we divide by x plus y squared, right? So you got that, right? This. Which means if we choose the term m equal 1, okay, so we get right from our node. Okay, then from this we also have two conditions, right? And this term is also bounded, which is less than 1. So from this we can conclude that, right? So from the 1 and 2, okay, now we can conclude that, right, the limit of the function h also equals 0, okay. So that means that, right, this is also equals 0, right? It's true, okay. Okay, so now we finish two techniques. Okay. Then let's see more in the next EP. We have more techniques to find the limit, right? And then going to the definitions of the continuity. Okay, bye.